We introduced the evidential interpretation of Bayes' theorem in our last lesson, but in this lesson we're going to look at it in a little more detail, and we're going to focus on how we can use this interpretation to evaluate the relationship between a hypothesis and the observed evidence. There are two main goals in this lesson. First, I want you to be able to gain some confidence in using the evidential interpretation of Bayes' theorem and the mathematical formulas for Bayes' theorem, both the simple and expanded versions. You should also be able to recognize when Bayes' theorem helps show that evidence corroborates or disconfirms some hypothesis. In the previous lesson, we covered how the evidential interpretation of Bayes' theorem can be used to determine how well a piece of evidence supports some hypothesis. Before continuing with this lesson, it's worth making sure you have a handle on each of the probabilities involved in this formulation of Bayes' theorem, seen here as the probability of H given E. So that means knowing and recognizing the chance of observing the evidence, the prior probability, the likelihood, and the posterior probability. You should also feel comfortable substituting in new sentences for P and Q in both the simple and expanded versions of Bayes' theorem. This version with E, the evidence, and H, the hypothesis, is gotten from substitution in our original versions. We also learned that we could give an expanded version of Bayes' theorem by replacing the probability of E in the denominator using the law of total probability. So here we have stated the version of the law of total probability that gives us the probability of E, the probability that the evidence is true. To get that, we have to add together, here the formula tells us, add the probability that we see the evidence given that the hypothesis is true times the prior probability of the hypothesis to the probability that we see the evidence given the hypothesis is false times the prior probability that the hypothesis is false. That becomes our expanded denominator in the version of the Bayes' theorem down at the bottom. Our goal in using the evidential interpretation of Bayes' theorem is to determine the probability of the hypothesis given that we observe some evidence to be true. So we want to know what's the chance that the hypothesis is true given some evidence. The expanded version of Bayes' theorem using the evidential interpretation tells us that in order to solve for the probability of H given E, the probability of the hypothesis given the evidence, we need to know 4 values. So these are going to be the 4 numbers we need to know. The probability of E given H, that's the likelihood. The probability of H, that's the prior probability. The probability of E given not H, so the probability of the evidence given the hypothesis is false, and the probability of not H, the probability that the hypothesis is false. Let's look at an example that uses this evidential interpretation and the expanded version of Bayes' theorem. The example we're going to look at is based on an actual study, one where horses were shown pictures of human faces and seemed to distinguish between happy faces and angry ones. All the numbers in this example are made up, but the point is that they give you a sense of how Bayes' theorem can help us evaluate a hypothesis like horses recognize human emotions, and how plausible, how probable that hypothesis is given that some evidence is observed. I'll keep the expanded version of the evidential interpretation of Bayes' theorem up at the top as a reference. It's a guide to what values we need to find to calculate the probability of H given E, the probability of the hypothesis given the evidence. So first we're told that researchers are interested in whether or not horses can recognize human emotions. And before they run any experiments, they work with the assumption that horses are just as likely to recognize anger as not. So they're neutral on whether or not their hypothesis is true. So their hypothesis is horses recognize the human emotion anger in human faces. That's what H stands for. The probability of H, that's our prior probability, is estimated to be 1/2. Researchers estimate the prior probability of the hypothesis before they consider any evidence. And they think that the probability that the hypothesis is true and the probability that the hypothesis is not true, the probability of not H, those are both equally likely. They both have a 50% chance of being true, so we can write that the probability of H is 1/2 and the probability of not H is 1/2. Again, 1/2 is how we would write the chance of 50%. Researchers make the reasonable assumption that if horses recognize angry faces as angry faces, they should regard them as threatening in some way. In previous studies, researchers discovered that horses have this left gaze bias. That is, if they recognize a threat, 90% of the time they'll turn their heads to view it using their left eye. This part of the description of the experiment gives us the evidence that researchers take to support their hypothesis. The evidence is horses looking at an angry face from their left eye. So if researchers see the horses look at the pictures from their left eye, that's evidence that they recognize the emotion anger. This description also tells us the probability of E given H, the likelihood that we would observe that evidence if our hypothesis is true. That's given by the chance of a horse turning its head to the left, given that it perceives a threat, like anger. And that chance is 0.9, 90%. That value, the probability of E given H, appears both in the numerator and in the denominator of our formula. So now we know E given H, but if we look at the denominator, we also need to know the probability of E given not H. We learned from the experiment that if horses don't recognize any threat, they are equally likely to look at something from either their right eye or their left eye. So if no threat is detected, there is no left gaze bias. The probability of E given not H is the likelihood that we would observe that same evidence, the horses looking from their left gaze, if our hypothesis is false. So the chance of a horse turning its head to the left, given that it doesn't perceive a threat, is 0.5, because they're equally likely to look from the right or left eye. With all this information, we can now say what the chance is that the hypothesis is true, given that we observed the evidence. In other words, what's the probability that horses recognize the emotion anger in human faces, given that they look at angry faces with their left eyes? That's our probability of H given E. Well, we now have all the values we need in order to calculate that. We needed the probability of E given H. We determined that was 0.9. We needed the probability of H. That's 0.5. We needed the probability of E given not H, also 0.5, and the probability of not H, again, 0.5. If you need to, go back and check the reasoning that led to any of these values. Plugging in the numbers, we get 0.9 appears for the probability of E given H times 0.5, the probability of H, that's on the top. And then we need to multiply the probability of E given H times the probability of H as one of the terms in an addition. So notice that same term appears both on the top and the bottom, but because it's part of an addition, it doesn't cancel out. So we need to add 0.9 times 0.5 to 0.5 times 0.5. The probability of E given not H times the probability of not H. That gives us 0.45 over 0.45 plus 0.25, or 0.45 over 0.7, and that's about 0.64. What does it mean to say that the probability that horses recognize anger in human faces, given that they look at angry faces with their left eye, is 0.64? What does that number tell us about the relationship between the hypothesis and the evidence? On its own, the number 0.64 just says roughly that the hypothesis has a 64% chance of being true given the evidence. But what's often more interesting is not how likely the hypothesis is to be true given the evidence, but rather whether the evidence supports the hypothesis. So this case where we're looking at equine behavior is one where the hypothesis is corroborated by the evidence. The evidence supports the hypothesis, so it raises the chance that the hypothesis is true. The way that we read this off of the formula is that the posterior probability, the value that we calculated, is higher than our prior probability. Let's compare the prior probability and the posterior probability in the equine behavior example. Remember that initially researchers thought the hypothesis that horses recognize emotion to be just as likely false as true. They just didn't have any real evidence one way or the other, so they thought the hypothesis could just as likely be true as it was false. So they gave the probability of the hypothesis as just 0.5. But after observing the evidence of the horse's behavior, we were able to calculate that the chance of the hypothesis was true is higher. The probability of the hypothesis given the evidence is 0.64. So once we take our evidence into account, our confidence that the hypothesis is true goes up. We now think it's more likely to be true than we did initially. That suggests that that evidence supports the truth of that hypothesis. Here's another way we can look at showing that evidence corroborates a hypothesis. Take our simple version of Bayes' theorem. Again, we're using this evidential interpretation. The probability of H given E equals the probability of E given H times the probability of H divided by the probability of E. What we're going to do is divide both sides of the equation by the probability of H. That cancels out the probability of H on the right-hand side and gives us a ratio of the probability of H given E, the posterior probability, to the probability of H, the prior probability, on the left-hand side. So again, we have the probability of H given E over the probability of H, the posterior over the prior on the left side, and then we have the likelihood over the chance that the evidence is true on the right-hand side. That's the probability of E given H over the probability of E. To show that the evidence supports the hypothesis, we should see that the probability of H given E over the probability of H is greater than 1. And we determine it using the right-hand side of the equation. So we determine that ratio of the posterior to the prior from the probability of E given H to the probability of E. If that number is greater than 1, the evidence supports the hypothesis. So for example, take our equine behavior case. We were given that the probability that we saw the horses look from their left eye, given that they recognize the faces, would be 0.9. And we calculated that the probability of E, that was that long denominator given by the law of total probability, we calculated that that was 0.7. Well, that ratio 0.9 to 0.7 gives us 1.29. This number is not a probability because it's not between 0 and 1. It's just a measure of how well the evidence supports the hypothesis. And the higher it is, the higher than 1 it is, the better the evidence supports the hypothesis. Why would we look at this ratio instead of just comparing the probability of the posterior to the probability of the prior? Well, the benefit of this calculation is that sometimes what matters is not how likely the conclusion is to be true given the evidence. We don't really care about that 0.64 number in particular. What we really care about is whether and how well the evidence supports our hypothesis. This ratio is a good measure of that. In fact, some philosophers have said that the idea that a hypothesis has a 2/3 chance of being true is a kind of meaningless thing to say. Not all of them agree, but some do. But everybody agrees that the notion that evidence supports a hypothesis is important. So this ratio helps us see that evidence supports a hypothesis, regardless of how likely that hypothesis is given the evidence. Another benefit of this way of showing that evidence supports a hypothesis is that it helps us see what kind of evidence better supports it. We're going to focus on the probability of E, the number in the denominator on the right-hand side. By definition, the probability of E is going to be between 0 and 1. And since it's between 0 and 1, the lower it is, the bigger that whole ratio will be. So the higher that ratio of E given H to E is. That tells us that the lower the probability of the evidence is, the better the evidence supports the hypothesis. So when is the probability of the evidence lower? Well, the more evidence we have, and the wider variety of evidence we have, the less likely it is that we'll see all of that evidence independent of our hypothesis. So let's take an example of more evidence. It's less likely that we see several horses all look with their left eye than it is that we see just one horse do that. So there we have more evidence, and together they have a lower probability of happening. Similar reasoning applies to a wider variety of evidence. It's less likely that both a horse's heart rate rises and they look with their left eye than it is that they just look with their left eye. The reasoning in both of those cases uses the general conjunction rule. The more outcomes we conjoin, the lower the probability, because multiplying more fractions give us lower and lower probabilities for E. The lower the probability of E is, the higher that ratio is, the more it is above 1, so the better that evidence supports the hypothesis. Of course, researchers and scientists don't always encounter evidence that supports their hypothesis. Sometimes they find evidence that disconfirms it. That is evidence that makes the hypothesis less likely to be true. There are two ways that we can show evidence disconfirms a hypothesis, just like there were two ways we could show that evidence supports a hypothesis. They're essentially the opposite of what we've just looked at. One way of showing that evidence disconfirms a hypothesis is if the posterior probability is lower than the prior probability. So if we find out that the probability of H given E, the output of our use of Bayes' theorem, is lower than our prior probability that in thinking that H is true, that shows that the evidence counts against that hypothesis being true. We can also again look at this ratio of the posterior to the prior. If that ratio given by the probability of the evidence given the hypothesis and the probability of the evidence, that's less than 1, that tells us that the chance of observing that evidence given our hypothesis is lower than just the regular chance of observing that evidence. That tells us that that evidence just doesn't lead us to thinking that the hypothesis is true. So here are your key takeaways for how Bayes' theorem helps us evaluate how well some piece of evidence supports a hypothesis. If evidence supports a hypothesis, the posterior probability should be higher than the prior probability. We can also show that evidence supports a hypothesis if the ratio of the posterior to the prior is greater than 1. We learned that more evidence and more varied evidence better supports a hypothesis, and we determined that using the ratio of the posterior to the prior. And finally, we learned that evidence disconfirms a hypothesis, making it less likely to be true if the posterior is lower than the prior, or if the ratio of the posterior to the prior is less than 1. In the next video, we'll look at some different uses of Bayes' theorem. But instead of examining how well evidence supports a hypothesis, we're going to consider something slightly different: how well an inductive argument supports its conclusion.